Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Okay, so today we will continue with chapter 3 part 2. So basically last week we have covered chapter 1 part 1 and also a little bit of chapter part 2. Okay, so today we will cover chapter 2 part 2 subchapter 3.7 FM PM modulators. Okay, in the previous lecture, you have learned on the definition of uh, frequency modulation and also phase modulation. So basically, when we talk about angle modulation, it consists of FM, either FM or PM. Okay, and also last week you have learned how to draw the frequency spectrum. Okay, based on Bessel table, and also how to calculate for the bandwidth using Bessel rule, Bessel table, and also Cousin rule. Okay, so for today, today's lecture it is fully theory. Okay, so we will cover on the FM/PM modulator, and also transmitter and also transmitter and receiver. Okay, so you look at slide 13 over here. Previously, you already know that for a phase modulator, PM, the carrier instantaneous phase is proportional to the modulating signal. Okay, so PM modulator, the carrier instantaneous phase, which is theta t, is proportional to the modulating signal, Vt. Okay, actually this is VMT lah, modulating signal. Whereas for the frequency modulator, the carrier instantaneous phase theta t is directly proportional to the integral. Okay, we have an integration here to the integral of the modulating signal. Okay, so over here, considering the FM modulator. So if the modulating signal is Vt is differentiate before being applied to the FM modulator, the instantaneous phase is now proportional to the modulating signal or PM modulator. Okay, so what it means over here, if for example you have an FM modulator. Okay, so FM modulator is theta t directly proportional to the integral of the modulating signal Vt. Okay, but what happens if you differentiate the modulating signal first before it is being applied to the FM modulator? So basically, what happens if you differentiate this modulating signal? So it become dVt over dt integral. Okay, so basically this integration of dVt over dt, okay, it will become Vt. Okay, so this theta t directly proportional to the modulating signal is also the same as the equation for the phase modulator. So basically, if you have a differentiator plus FM modulator, you will actually the system actually acts as a PM modulator. Okay, so this is what it means by this statement over here. So if you have FM modulator but you differentiate the modulating signal first, then it will become a PM modulator. Okay, so next, but what happens if you have a PM modulator? So for a PM modulator, you know that theta t is directly proportional to the modulating signal Vt. Okay, but what happens if you integrate the signal Vt before it is being applied to the PM modulator? So this will become theta t directly proportional to the integral of Vt. Okay, so this is actually the same as the FM modulator. So basically integrator plus a PM modulator, it is actually the same as FM modulator. Okay. So basically for FM PM modulator, we have two types. The first one is direct FM modulator. The second one we have indirect FM modulator. Okay, so this figure over here is an example of a direct FM modulator, a simple direct FM generator. Okay, so from this figure, so you can see that this is your sound source. Okay, sound source, the signal that you want to send. Okay, and in the circuit you have a tank circuit. Okay, so this tank circuit actually consists of the capacitor and also the integrator L. Okay, L and Cm. Okay, so the function of this tank circuit is for frequency determining components. Okay, so the function of this capacitor is actually to convert acoustic energy. The sound source is in acoustical energy. So convert acoustical energy into mechanical energy. Okay, so which it is used to vary the distance between the plates of Cm. Okay, so for capacitor, you know that we have two plates like this. So when the acoustical energy is converted to mechanical energy, basically the distance of this plate will vary. So when the distance of this plate varies, then it will change the value of the capacitance. Okay, so when the value of the capacitance is varied, Cm is varied, then the resonant frequency is varied. Okay, so this is what happens in a direct FM modulator. So this is how it changes the frequency, okay, of the carrier signal to follow the modulating signal. Okay, so example of direct FM modulator, we have varactor diode modulator. Okay, so this is an example of direct FM modulator, and this is the circuit. Okay, so basically for the varactor diode modulator, so here this is the modulating signal input, the signal that you want to send, and in the circuit you have R1 and also R2, where the function is to develop DC voltage that will reverse bias the varactor diode VD1. Okay, and it will actually determine the resonant frequency of the oscillator. Okay, so this is so the external modulating signal voltage added or subtracted from this is bias, which changes the capacitance of the diode and consequently changes the frequency of the oscillation. Okay, so if you compare this statement with the previous statement, this is a general statement on direct FM modulator. So basically you can see that how it controls the frequency is based on the value of the capacitance. Okay, so when the value of the capacitance changes, then the frequency of oscillation will also changes. Okay, so this is general how this circuit works. Okay, it changes the value of the capacitance in the circuit, therefore the frequency also will changes. Okay, so basically you don't need to go into detail on the process of the varactor diode modulator itself. Okay, you just need to know in general, okay, how direct FM modulator and indirect FM modulator works. Okay, so next, another example of direct FM modulator, we have the Vco Fm Modulator, and this is the circuit. Okay, so if you look at here, from this circuit you can calculate for the Fc, okay, the center frequency of the oscillator, which is 1/2 pi square root Lc. Okay, so from this formula you can see that the Fc is affected by the value of C. Okay, so this is similar to the previous statement that I explained to you, that for FM modulator, how it changes the Fc or the carrier frequency is by it changes the value of the capacitance in the circuit. Okay, so when the modulating signal is applied, the frequency Fc will become this equation, where delta C is the change, okay, the change that happens in the varactor diode capacitance due to the modulating signal. Okay, so when there is a changes, then there will be frequency changes also, and you can also calculate for the frequency changes, which is delta F, which is equals to Fc minus F. Okay, so next, let's look into frequency up conversion. Okay, so this, okay, before the frequency up conversion, we have the indirect FM modulator or direct PM modulator. Okay, so what is the difference between direct FM and indirect FM? Okay, so indirect FM is where we look in terms of the phase deviation instead of the frequency deviation. Okay, so look at here, for indirect FM, the instantaneous phase deviation is directly proportional to the modulating signal. So instead of we look at the instantaneous frequency, now we look at the instantaneous phase deviation, where it must be proportional to the modulating signal. Okay, so the indirect FM is accomplished by directly changing the phase of the carrier, and this is the circuit for the varactor diode modulator. Okay, so this varactor diode modulator, so it has a VD1 varactor diode, which is placed in series. So you look at here, it is placed in series with the inductive network, which consists of the L1 and also R1, and this combined series parallel network, okay, it appears as a series resonance circuit to the output frequency from the crystal oscillator. Okay, and the advantage of indirect FM, okay, the advantage of indirect FM is that it is more stable compared to the direct modulator. Okay, so this is important. What is the advantage of indirect FM compared to direct FM? So indirect, it is more stable, however, it has more distortion in the modulated waveform compared to the direct FM modulator. Okay. So next is the frequency up conversion. Okay, so this is one of the important subchapter in chapter 3 part 2. Okay, so what is frequency conversion? Okay, so over here is stated that after the modulation process, the frequency of the modulated wave will be up converted. Okay, where the frequency will be increased to a desired frequency of transmission. And there are two ways how we can perform the frequency up conversion. So the first one is by using the heterodyning process. The second one is by using frequency multiplication. Okay, so what is the difference between heterodyne process and frequency multiplication? So if you look at this block diagram, so this is the block diagram for heterodyne process or heterodyne method. So if you look at here, this is the input from FM or PM modulator. So the input from FM PM modulator, we have this parameter. We have the carrier frequency, the frequency deviation delta F, the modulation index M, the modulating signal frequency FM, and also the bandwidth. Okay, so how can we actually increase this value Fc? Okay, so for heterodyne, we need what we call as the balance modulator. Okay, so you have a balance modulator where you inject a new signal. Okay, so this new signal we call as RF frequency, FRF. Okay, so this RF oscillator is the ones that generate the FRF. Okay, so when FRF and this inputs from the FM or PM modulator goes into the balance modulator, the output, okay, you will have Fc at the output is equals to Fc at the input plus, you must plus with the FRF. Okay. However, for the rest, okay, the other parameters, delta F, the modulation index, the FM, and also the bandwidth, it is unchanged. Okay, so or it is unaffected by the heterodyne process. So the heterodyne process, it only affects the value of Fc. Okay. So this one I've already explained. So you can see that for the balance modulator, you have two inputs. One input is from the FM PM modulator, and another input is the unmodulated RF carrier signal that we generate. Okay, so you can see that the ones that is affected is only the Fc. And the rest, the frequency deviation, the rate of change, modulation index, phase deviation, and bandwidth are unaffected by the heterodyne process. Okay, so this is how we can increase the value of Fc, how we can do the frequency up conversion. Okay, the second method is the multiplication method. So for the multiplication method, instead of having a balance modulator, now we have a frequency multiplier. Okay, so the input to the frequency multiplier is the same. It is the input from the FM or PM modulator. So you have this parameter, you have Fc, delta F, M, FM, and also the bandwidth. But now the difference is, at the output, okay, your Fc out at the output is now you need to multiply with the multiplier n. Okay, so Fc out is equals to n multiply with Fc in, delta F out multiply equals to n multiply with delta F in, M out equals to n multiply with M in. Okay, so Fc delta F M you need to multiply with n. However, for Fm, it is unaffected by the multiplication process. And in the multiplication process, you should know that the bandwidth at the output is bigger compared to the bandwidth at the input. Okay, so why the bandwidth at the output is bigger than the bandwidth at the input? It is because you know that the frequency deviation and modulation index are also multiplied with the multiplier n. So therefore, if you remember the Bessel table, So if your modulation index increases, the number of side frequency in your frequency spectrum will also be increases. Therefore, the bandwidth will also increases. Okay, so if you have higher modulation index, then you have the number of side frequencies will also increases. So therefore, you should know that the bandwidth, this is the bandwidth, will also be increased. Okay, so you can calculate the bandwidth at the output by using the Carson rule, n multiply with 2 delta f, or n multiply with b in. Okay, so why do we need to know the process of these two methods, heterodyne process and also the multiplication process? Okay, because it will be used in the FM transmitter. Okay, so now let's look at subchapter 3.9, which is FM transmitter. So FM transmitter, we have direct FM transmitter and also indirect FM transmitter. So this is example of a commercial broadcast band direct FM transmitter. Okay, so if you look at here, this FM direct FM transmitter, it is also known as the Crosby direct FM transmitter, and you can see that you have the AFC loop over here. This is what we call as the AFC loop, or the automatic frequency control, AFC. Okay, automatic frequency control loop. So if you look at here, this is your modulator. This is your first input, which is the modulating signal input. And the input here is the input that we generate, the FC. Okay. So the FC here is 5.1 megahertz. Okay, this is 5.1 megahertz. Okay, which is multiplied by 18 to produce a final transmission carrier FT 91.8 megahertz. So for example, since your frequency FC at this point over here, it is equals to 5.1 megahertz. But if, for example, at the output you want it to be 91.8 megahertz, then you should have this frequency multipliers. You must multiply the FC with 18. Okay, so that is why you have these three multipliers. 3 multiplied with 2 multiplied with 3 is equals to 18. Okay, so 5.1 multiplied with 18, you will get 91.8 megahertz. And take note that this is the multiplication process that you have learned in 3.8. Okay, this block here, this is the multiplication process, this one. Okay, so remember, for the multiplication process, the parameter that is affected is FC, delta F, M, and also B. Okay, but the parameter that need to be multiplied by the multiplier N is FC, delta F, and the modulation index M. Okay, so that is why it is stated here that the frequency and phase deviation at the output of the modulator are also multiplied with 18. Okay, because this is the multiplication process. But if you have a heterodyne process, you must take note that only the value for FC changes. Okay, so look at here, to achieve maximum deviation allowed for FM stations at antenna, which is 75 kilohertz, the deviation at the output of the modulator is, okay, you know that you can use this formula, So delta F is equals to 75K divided by 18. So you will get 41.66.7 Hertz. Okay, so this is for the frequency deviation. Okay, and you can calculate for the modulation index M. So you know that M is equals to delta F over Fm. So previously you have calculated the delta F equals to 4166.7. So divide with Fm. So your Fm is for a maximum modulating signal frequency allowed for Fm, it is 15 kilohertz. So you just divide with 15K. So you will get the modulation index equals to 0.2778. Okay. So remember, for direct FM transmitter, you have the AFC loop. This loop over here. This loop is it generates the FC, carrier frequency, as one of the input to the modulator. Okay, but why do we need FFC loop instead of having just a direct reference oscillator FC? Okay, why do we need all of this for the direct FM transmitter? Okay, so you should know that this direct FM transmitter, the stability of the oscillator is low. Okay, so in order to overcome the instability, this AFC loop is used. Okay, so this is important. Why do we need AFC loop in a direct FM transmitter? Okay, to overcome the problem of stability caused by the crystal reference oscillator to generate the carrier frequency. Okay, so that one is direct FM transmitter. This is the indirect FM transmitter. So it is indirect because the phase deviation, this is indirect because the phase deviation is the one that is directly proportional to the modulating signal. Okay, so this is an example of an indirect FM transmitter, which we call as the Armstrong Indirect FM Transmitter. Okay, so if you look at here, this is the modulator. So the input of the modulator, we have two. So the first one is the modulating signal input, the signal that you want to send, FM, and also another input, this one over here. So this is the FC, carrier signal, 200 kilohertz. Okay, so the output of the modulator will go to the combining network and then to the bandpass filter. So if you look at here, after the bandpass filter, we have the multiplication process. Okay, you need to multiply with 72. And after the multiplication process, look at here, we have the mixer and down converter. This is what we call as the heterodyne process that you have learned previously. Okay, so remember, for heterodyne process, you need two inputs. Okay, so one input here, this is the output from the multiplier, and another input is the input that we generate, okay, from the crystal oscillator here. Okay, so but you must take note that in the previous slide that I've shown you for the heterodyne process, that one is up converted. Okay, so up converted meaning you need to add the frequency. But over here, it is down converted. So when it is down converted, it means that the frequency is actually being reduced. So therefore, you need to minus the frequency, this F1, minus with the frequency F0 that is generated by the crystal oscillator. Okay, then the output goes to the bandpass filter, and then you have the multiplication process again, multiply with 72. bandpass filter, power amplifier, then only it will go to the antenna, send to the receiver. Okay, so from this figure, you can actually see the importance. Why do we need to know the heterodyne process and the multiplication process that we have learned in the previous slide? Okay, because you should know which parameters is affected. Okay, so for example, at this point over here, okay, at the output of 7 multiplier, okay, so you must make sure that the parameter Fc, delta F, and also the modulation index must be multiplied with 72. But the output from the heterodyne process, okay, only the frequency is affected. Okay, so you don't need to there will be no changes in the delta F, M, and also Fm. Okay, so this one is just to show you that from the general equation for the angle modulation, this is the general equation for the angle modulation. Okay, by using this trigonometric function cos A plus B, cos A equals to cos A cos B minus sin A sin B. Okay, so you can write this equation like this. Okay, by using the trigonometric equation. Okay, so from this equation, if for example you have a very small modulation index, then your equation will become cos m cos omega ct. Okay, so if modulation index is very small, this will become cos 0. So cos 0 is equals to 1. Okay, and sine m cos omega mt will become m cos omega mt. So therefore, from this equation, it will become something like this. Okay, so basically you can write the angle modulated with mt equals to Vc cos omega ct minus Vc m sin omega ct cos omega mt. Okay, so now let's look at the example for the indirect FM transmitter. Okay, so this is example on the Armstrong indirect FM transmitter. This block diagram. Okay, so if you have your notes with you, you can actually refer this figure while we do the example. This example. Okay, so consider a 200 kilohertz carrier being phase modulated with a 15 kilohertz modulating signal, which will produce modulation index of 0.00096. Okay, so look at here, the Fc is 200 kilohertz. Your Fm is 15 kilohertz. So if you refer to this figure, you can see that the Fc is 200 kilohertz and your Fm is 0 to 15 kilohertz. So that's why we write Fm equals to 15 kilohertz. Okay. So you will get modulation index equals to 0.00096. Okay. And also you can calculate for the frequency deviation delta F. Okay, so you know that M is equals to delta F over Fm. So delta F is equals to MFM. So 0.00096 multiplied with 15 kilohertz, you will get 14.4 hertz. Okay, so this is the frequency deviation at the output of the combining network. Okay, this is the frequency deviation delta F at the output of the combining network. So delta F at this point here is equals to 14.4 hertz. Okay. So this statement stated that in order to achieve the required 75 kilohertz deviation for the FM broadcast at the antenna, the frequency must be multiplied with 5208. Okay, so why F208? Because you want to achieve delta F equals to 75 kilohertz at the antenna. Okay, but currently your delta F at the output of combining network is only 14.4 hertz. Okay, so how can we actually increase from 14.4 hertz to 75 kilohertz? So 75k divided by 14.4, you will get 5208. So basically you need to multiply with 5208 in order to achieve 75 kilohertz at the antenna. Okay, so however, the problem is if you directly multiply with 5208, okay, remember for the multiplication process, okay, you need to multiply with n. So the parameter that is affected, okay, when you multiply, this ft will also be affected. Okay, so therefore the frequency you need to also multiply with 5208. Okay, so previously your FC is 200 kilohertz. Okay, so at the antenna you must multiply it with 5208. So your frequency FC or FT at the antenna will become 1041.6 megahertz. And the problem is that this value is beyond the limit for the commercial FM broadcast band. So the limit for commercial FM broadcast band is only from 30 to 300 megahertz. So therefore, you cannot directly multiply with 5208. Okay. So how to solve for this? Okay, that is why you can see that in the Armstrong Indirect Fm Transmitter, instead of having only multiplication process, but in the circuit, it used a combination of multiplication process together with the heterodyne process. Okay. So if you look at here, so let the output waveform of the network is multiplied by 72, producing the following signal. F1 equals to, this is FC multiplied with multiplier. F1 is equals to 72 multiplied with 200k, you will get 14.4 megahertz. And your modulation index also you need to multiply with 72. And delta F also you need to multiply with 72. Okay. So basically so then after the multiplication process, this one, after the multiplication process for the first multiplier, okay, the signal will go to the heterodyne process or the mixer and down converter. Okay, so if you look at here, in the mixer down converter, the frequency of FO is given by 13.5 megahertz. Okay, so therefore the output of the mixer and down converter will become 14.4. This 14.4 minus the FO 1315 megahertz. Okay, so why do we need to minus? Because it is a down converted. If, for example, it is a up converted, then instead of minus, you need to add. Okay, so now the value F2 is equals to 1.25 megahertz. Okay, so but look at here, since this is a heterodyne process, you can see that only the frequency is affected. The modulation index and also the frequency deviation remains unchanged or unaffected. Okay, so after the mixer and down converter section, we have another multiplier. This one, the second multiplier over here. Okay. So the signal from the mixer and down converter will go to the second multiplier, where you need to multiply by 72. Okay, so since this is a multiplication process, all of these parameters need to be multiplied with 72. Okay, so the final frequency at the antenna is equals to 90 megahertz. Modulation index is 4.98 radian, and delta F is equals to 74.65 kilohertz. Okay, so you can see that by combining the process of multiplication and heterodyne, okay, you can actually achieve this requirement where you want the delta F to be 75 kilohertz. Okay, look at here. The requirement is your delta F at the antenna must be 75 kilohertz, and your frequency at the antenna must be within this range. Okay, so you can see that now the frequency is 90 megahertz, so it is within the range, okay, between the range 30 and 300 megahertz, and the delta F is 74.65 kilohertz, which is approximate to 75 kilohertz. Okay, so you achieve these two requirements by using this indirect FM transmitter. If you direct multiply with 5208, you can achieve this 75 kilohertz, but the value FT is beyond the limit of this commercial FM broadcast band. Okay, faham eh? So this is very important for you to understand, okay, how the indirect FM transmitter works, which consists of the multiplication process and also the heterodyne process. So now let's look into the FM receiver. So this is transmitter. Now let's look at the FM receiver. Okay, so this is the block diagram of an FM receiver. Okay, so this is double conversion super heterodyne FM receiver. I think you have learned on double conversion process in the previous lecture. Okay, you have covered on this. So why it is called double conversion? Because you can see that it has two intermediate frequency. Okay, and for this FM receiver, you can see that you have the AGC, automatic gain control. This is the automatic gain control. So it is used to prevent mixer saturation when strong radio frequency signals are received. And also you have the peak detector stage over here, which consists of the limiter, frequency discriminator. So this frequency discriminator is actually the demodulator, yeah, and also the de-emphasis network. Okay, so if you look at here, so the function of the limiter, this one, is to remove amplitude variation caused by noise. Okay, so you know that the amplitude variation caused by noise is one of the disadvantages of amplitude modulation. Okay, so by adding the limiter in frequency modulation, so basically FM has a better amplitude variation compared to caused by noise compared to AM. Okay, and the second one, we have the frequency discriminator or the demodulator. So the function is the same as the previous lecture. The function of demodulator is to extract back the information from the modulated wave, okay, to get back the original signal. Okay, and after the demodulator, you have the de-emphasis network, which contributes to the improvement in the signal to noise ratio. So remember, in the previous slide, it is stated that this is the double conversion process because you have two intermediate frequency. Okay, so basically the first intermediate frequency is consists of high frequency in order to have a good image frequency rejection. Okay, so what is image frequency? This one is also you have learned in chapter 3 part 1 if I'm not mistaken. Okay, and the second intermediate frequency actually consists of a low frequency, and this to allow the amplifiers to have high gain and also to improve the system stability. Okay, so this is FM demodulator. So FM demodulator is used to produce an output voltage that is proportional to the instantaneous frequency at its input. So this is the transfer function, overall transfer function for the FM demodulator. KD equals to V over F, and if you want to calculate for the output from the FM demodulator, it is V out equals to KD multiplied with delta F. So KD is this one, V over F. Okay, and so for FM demodulator, the most commonly used circuit is the slope detector, balance slope detector, and also PLL demodulator. So take a look here. For the balance slope detector and also PLL demodulator, it is categorized as the tuned circuit frequency discriminator. Okay, so before we continue with the tuned circuit frequency discriminator, so let's try and do this example. For an FM demodulator circuit with a transfer function of KD equals to 0.2 and an FM input signal with 20 kHz of peak frequency deviation, determine the peak output voltage. So this one you just use the formula V out equals to KD delta F. So your KD is 0.2 V over kilohertz, and delta F is 20 kilohertz. Okay, so 0.2 multiply with 20, you will get 4 volt, because you can cancel this. So 0.2 multiply with 20, you will get 4 volt. So the output, the answer is the peak output voltage is equals to 4 volt. Okay, so remember this FM demodulator, slope detector and balance slope detector is categorized as tuned circuit frequency discriminator. Okay, so for further information on this, you can read the slide in slide 39, 40, 41 and 42. Okay, but I don't want to go into details in the process for the tuned circuit frequency discriminator. So basically this part 3.11.1 will not be asked in your test or in your final exam lah. But the ones that you need to know is this one, the comparison between the slope detector and balance slope detector. Okay, so you can see that over here, even though slope detector is simple and the balance slope detector is complex, okay, however, the balance slope detector, it is better in terms of linearity and tuning, and it does not need limiter stage. Okay. And this one you can also read by yourself, the PLL FM demodulator. You can go through this, roughly read this, okay, but you don't need to know in details how it works. Okay, so any question? Faham tak? Do you understand today's lecture? Faham? Okay, fully
Faham.
pure.
Nanti kalau saya tak tahu nanti saya tanya balik tu.
Okay, so fully theory hari ni. So remember, you have your test. When is your test?
30 is it?
30, yeah. 30, Don't forget that you have a test on 30th April, this Friday, 8:30 p.m. So it will cover chapter 1 and chapter 2 only. Okay, so 1 hour 30 minutes for you to answer, and I will add another because the other class requested for extra 10 minutes to upload. Okay, so maybe your total will be around 1 hour 40 minutes. Okay, so your test, I will upload it in the Ulearn. Siapa ya? Any more question?
PM AM nah doktor.
PM AM?
Is it pagi ke malam?
Oh, malam.
Malam.
Saya ingat amplitude modulation, phase modulation tadi.
Bukan doktor, bukan.
Okay.
Okay.
Malam 8:30 PM. So I hope jangan lupalah, because in your ada yang quiz hari tu, ada yang mesej saya tertinggal. So saya harap for the test semua available lah at that time. Okay, so if you miss the test without a valid reason, so there will be no retest. Okay, so so next week we will continue with chapter 3 part 3, and also we will discuss on your test. Okay, your test 1. Okay, and the next another 2 weeks is your midterm break. Okay, so after midterm break, then only we will start with chapter 4. Okay, so any question?
No, tak.
Doctor.
Okay, so no question. So Good luck for your test, and we'll see you to next week. Okay.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Thank you, Doctor.